In this video, we're going to begin introducing the methods for numerical integration. And in particular, we're going to be talking about the rectangle method. So let's consider a function f defined on an interval from a to b. The rectangle method utilizes the Riemann integral definition to calculate an approximate estimate for the area under the curve by drawing many rectangles with very small width adjacent to each other between the graph of the function f and the x-axis, similar to the image shown here. For simplicity, the width of the rectangles is chosen to be constant. So let n be the number of intervals going from a to b. So a is equal to x0, and then up to xn, which is equal to b, with a constant spacing h, which is equal to xi plus 1 minus xi. The rectangle method can be implemented in one of the following three ways. So I1 approximates the integral from a to b of f of x dx as h times the sum of f of x minus I. The second method uses h times the sum of f of x minus I plus xi over 2, so the midpoint between xi minus 1 and xi. And the third method uses h times the sum of f of xi. And so we'll go through what the difference between each of these are. So if xi minus 1 and xi are the left and right points defining rectangle number I, then the first method of the rectangle rule, so I1, assumes that the height of the rectangle is equal to the function evaluated at xi minus 1. So the integral for that one interval is approximated as the area of that rectangle. So it's h, so this distance here is h multiplied by the height, which is f of xi minus 1. And then the integral over the full domain, we just add up the area of all of those rectangles, so it's equal to h times the sum of f of xi minus 1, where I goes from 1 to n. The second method, again, we have the same interval, so xi minus 1 and xi are the left and right points defining the rectangle number I. Then I2 assumes that the height of the rectangle is f of xi minus 1 plus xi over 2. So it's instead evaluated, again, this is going to be equal to h again, and we're evaluating the height of the rectangle at the value of the function at the midpoint of the rectangle. And this is because of that known as the midpoint rule, and it is the most common implementation of the rectangle method. So for the one rectangle, the area or the integral is approximated as the area of this rectangle, which is just h times f of xi minus 1 plus xi over 2. So then over the whole domain, the integral is approximated as the sum of the area of all of those rectangles. So again, they all have a width h, and then multiplying by their respective height, which is evaluating the function at the midpoint of the rectangles. And then the third one assumes that the height of the rectangle is given by the value of the function at xi. So here the rectangle is now hitting the top right edge, or it hits the function at the top right edge. So again, for one interval, the integral is approximated as the area of this rectangle. So again, this is h, and then multiplied by the height of the rectangle, which in this case is f of xi. So to get the integral over the whole domain, we approximate this as the sum of the area of all those rectangles. So h times the sum of f of xi. So let's look at just a quick example to see kind of the difference between these methods. So consider the function f of x is equal to x squared on the interval from 0 to 1. The exact integral we can calculate, so x cubed over 3 evaluated between 0 and 1 is just equal to 1/3, or 0.3333. And these images show the implementation of the rectangle method using the three different approaches. So here I1 is equal to 0.24, I2 is equal to 0.33, and I3 is equal to 0.44. And you can see kind of where those rectangles meet the function and for the different implementations. And in particular, you can notice for the midpoint rule that we actually get quite a good estimate of the integral, and basically kind of how this one works is that this area that we're sort of overestimating in one spot tends to cancel out with the area that we are underestimating in the next spot. And so we end up with a pretty good estimate, even though it doesn't follow the function exactly. So for I1, each rectangle touches the graph of the function at the top left corner of the rectangle. For I2, each rectangle touches the graph of the function at the midpoint of the top side. And for I3, each rectangle touches the graph of the function at the top right corner of the rectangle. So we can talk about error analysis for all of the methods that we're talking about here. So we can arrive at an error analysis by using Taylor's theorem. So this can help us to find out how the error changes as the step size h decreases. So first let's consider I1, and the same analysis will apply to I3, so we'll only go through it once. So the error in the calculation of the rectangle number I between points xi minus 1 and xi will be estimated as we go through here. And we're going to go through it with the first method, and again, as I said, it also applies to the third method. So for rectangle I between xi minus 1 and xi, using Taylor's theorem, we can say that for every x in our interval, there exists a value c, which is between xi minus 1 and x, such that f of x is equal to f of x minus 1 plus f prime c times x minus xi minus 1. So this is just the Taylor expansion of our function, f of x, with about the base point xi minus 1. So if you recall from our Taylor expansion, basically the first term here is the Taylor polynomial, and this term with the c is the remainder term. So we can use this to kind of help us understand the order of accuracy and the error associated with the rectangle method. So the error in the integral using this rectangle is shown here. So the absolute value of EI, so just for the one rectangle, is the integral of from xi minus 1 to xi of f of xi, or f of x minus f of xi minus 1. So it's the integral of the function minus our approximation. So this is just rewriting that, and we know that from the expression written on the previous slide that if we rearrange that equation, this part we can replace with this f prime c times x minus xi minus 1. And then we can do this integration to get the expression shown here. And so if you recall kind of the procedures that we went through in the chapter 3 with the Taylor series, the upper bound of the error for the integral on the rectangle I is given by this expression here. So the absolute value of EI, so E on one rectangle, so one interval, is less than or equal to the maximum of C in xi minus 1 to xi. So C can take any value within the interval, and the value that you choose is the one that maximizes the upper bound of the error estimate, times, or so the maximum of the absolute value of f prime c times x minus xi minus 1 squared over 2 evaluated at the end limits of our interval. So basically all we've done here is, if this was our estimate of the error, then this gives the upper bound of that estimate. And then we can plug in the limits, which came from our integration, and this term goes to 0. So we can simplify this, and we see that on the one interval, the upper bound of the error for the rectangle method is related to h squared over 2. So that was for one interval. Then if n is the number of subdivisions, the number of rectangles, or which is also the number of rectangles, so nh is equal to b minus a if our total domain was from a to b. When the area of the integral over the total domain is equal to absolute value of e, which is n times ei. So basically we just add up the errors for all of the intervals. So then we can basically multiply our previous expression here by n, and we know we can plug in the relationship between n and h in terms of b and a. So the total error for the over the whole domain is this max of f prime c times b minus a times h over 2. So this means that the total error is bounded by a term that is directly proportional to h. So when h decreases, the error bound decreases proportionally. And of course, when h goes to 0, the error goes to 0 as well. So for the entire domain, the first and third versions of the rectangle rule are first order accurate. And you'll notice that, and this will come time and again when we go through this error analysis, that the error over a single interval was proportional to h squared, and then the error over the entire domain was one order less than that, so in this case proportional to h. And that's because as you include the entire domain, you're adding up the errors over each of those intervals, and so you end up, in this case, being first order accurate. Okay, so let's consider I2, which is a little bit different than the other ones. So this was the midpoint rule. So the midpoint rule provides a more accurate approximation, since the error for the entire domain is going to be bounded by a term that is directly proportional to h squared, as we will see here. So for a rectangle I between xi minus 1 and xi, using Taylor's theorem, we can say that for every x in our interval, there exists this value xi between xi minus 1 and x, such that we have this expression here. So if xm is equal to xi minus 1 plus xi over 2, so the midpoint between xi minus 1 and xi, then we can write, basically using our Taylor expansion of a function f of x about our base point xm. So f of x is equal to f of xm plus f prime xi times x minus xm plus this remainder term f double prime c times x minus xm squared over 2. So, so our approximation for our integral is just still this first term. So the error in the integral using this rectangle is shown here. So it's basically the difference between f of x and f of xm. So we can plug in, we can rearrange this equation and plug in all these values into this expression. So that's what we've done here. So basically we rearranged this and said that f of x minus f of xm is equal to all of this. So we put this in here. Now we can do this first integral, expand that out, and this is going to be equal to 0. If you go through and basically because xm is the midpoint between xi minus 1 and xi, if you put that in and you go through and expand out that, do that algebra, you'll see that that goes to 0. So what we're left with is, if we do this integration here, we're left with this expression. And that's just rewriting that, and we can say now, so if that's our expression for our error, then the upper bound of the error for the integral on rectangle I is given by absolute value of ei is less than or equal to this max of c in our interval of f double prime c over 2 times h over 2 cubed minus negative h over 2 cubed, all divided by 3. So we can simplify that down, and we see that it is related to h cubed over 24. So for one interval, the midpoint rule is third order accurate. So again, just rewriting that, this was for one interval. So if n is the number of subdivisions or the number of rectangles, so nh is equal to b minus a, then the error of the integral over the total domain is given by n times ei. So that was max of c in our total interval a to b of f double prime c times n times h cubed over 24, which can be simplified down to the expression shown here. So we've got b minus a h squared over 24. So the total error is bounded by a term that is directly proportional to h squared, which provides higher accuracy than I1 and I3. So for the entire domain, the midpoint, or the second version of the rectangle rule, is second order accurate. So you can see that it is more accurate than the other implementations, and it is, because of that, it is the most common implementation of the rectangle rule. So let's look at an example. So let's use the rectangle method with n equals 4 to calculate the three different implementations, I1, I2, and I3, and compare with the exact integral of the function f of x is equal to e to the power x on the interval from 0 to 2. And then we can find the values of h required so that the total error obtained by I1 and I2 are bounded by 0.001. So find the different values of h for those two different methods that would allow our maximum upper bound of the error to be 0.001. So first, with n equals 4, the spacing h is calculated as shown here. So h is equal to b minus a over n. So in this case, h is equal to 0.5. So then we can, if h is equal to 0.5, then we have all of our data points at a spacing of 0.5, and we can find the function values at all of those data points as shown here. So then, according to the rectangle method, for I1, we've got the sum as I goes from 1 to n of f of x minus I h. So that's just equal to the h was our 0.5, and then these are all of the function values at all of the x times, or x of I minus 1s. So this means our I1 is equal to 4.924. I3 is very similar, except instead we're going to be evaluating at xi instead of xi minus 1. So that is all these values shown here, and so our I3 is 8.119. Now for I2, we need to calculate the values of the function at the midpoint for each rectangle. So that's what is being done here. So the midpoint of all the rectangles is, so for example, x0 plus x1 over 2. And so evaluating that, the function at those values. So the expression for I2 is the sum as I goes from 1 to n of f of xi minus 1 plus xi over 2, evaluating the function at the midpoint of the interval, times the width of the interval, which is h. So just plugging in all of our values, we can see that I2 is equal to 6.323. And the exact integral is just e to the x evaluated between our limits, so 0.638906. So I2 provides a pretty good approximation with only 4 rectangles. And this shows graphically what the 3 different implementations look like with the values of the integrals listed here. So let's take a look at the error bounds. So the total errors obtained when h is equal to 0.5 are indeed less than the error bounds obtained by the formulas that we went through earlier, and we can see that here. So for I1 and I3, the error estimation is bounded by the expression shown here. So if we plug in our values, so our b and a is 2 minus 0, h is 0.5, and then what we need to plug in, so the derivative of e to the x is just e to the x, and the value of c that maximizes that within our interval is just going to be 2, so that's why we have e to the power 2 here. So that means our upper bound of our error is 3.695. And the errors for our estimate number 1 and number 3 are shown here, which are indeed less than this upper bound. So the same formula can be used to find the value of h so that the error is bounded by 0.001. So if we know that this is our estimate of the upper bound of our error, we can use this to calculate h. So in this case, h is 0.000135. So to guarantee an error less than 0.001 using I1, the interval will have to be divided into 14,778 rectangles. And if we do this, we get the estimate of the integral is 6.38862, which provides an error less than 0.001, as we can see, 0.000432. And this is the kind of graphically how it looks, and you can see that it really represents the function really well, and it represents the area under the curve really well. We can do the same thing for when for I2. So when h is 0.5, the error in the estimate using I2 is bounded by the expression shown here, which for our case means that the error should be less than 0.1539. And if we calculate the actual error, it was indeed bounded by that, so it's 0.06606. So we can use the same formula to find the value of h so that the error is less than 0.001. So this was the expression for the error for I2, so we can use this and solve for h. So in this case, h has to be 0.04. So to guarantee that the error is less than 0.001 using I2, the interval will have to be divided into 50 rectangles. And this shows the implementation of that, which results in an error of 0.000426.